Welcome to iLecture Online, and today, continuing with physics in terms of fluid dynamics, we're now going to talk about a topic which is very interesting, very practical, and sometimes very confusing. It's called Bernoulli's equation. It has to do with fluid flow, and typically fluid flow through a pipe, but it can also be applied to other examples. And because there's so many different applications, I'm going to show you a set of examples. I have planned 7 examples of how we can look at Bernoulli's equation. So you may say, what is Bernoulli's equation? Now, we're not going to derive the equation, but let me say what Bernoulli came up with. He took the pressure in a fluid, the velocity in a fluid, and the height of the fluid relative to some reference point into an equation so that we could relate those 3 concepts to each other. So pressure, velocity, and height of the fluid all are related to one another, and he put it together into what he called Bernoulli's equation. But starting out, we're going to say that the pressure at any point inside the pipe plus rho gh of the fluid, now rho would be the density of the fluid, g is of course acceleration due to gravity, and height is the height above some reference point, plus 1/2 rho v squared. Again, rho is the density of the fluid and v is the velocity of the fluid through the pipe. And again, it doesn't have to be through a pipe, but for simplicity, let's start there. And he said that those 3 terms combined are always constant. So, which means that if one increases, something else has to decrease. For example, when the pipe gains height, so that this term becomes bigger, something else has to become smaller. Now, in this particular case, since the pipe doesn't change in diameter, the velocity at point 1 must equal the velocity at point 2. So we know that that must be the same no matter what. And since this will increase, the only other option that we have is that the pressure then will decrease over here because of its increased height. And that's how Bernoulli was able to manipulate what happens in fluid flow. Now, let's write down the equation. So at point 1, we can say pressure at point 1 plus rho gh at 1 plus 1/2 rho v at 1 squared must equal, since it's constant, to these 3 terms combined at point 2. So we can say pressure at 2 plus rho gh at 2 plus 1/2 rho v2 squared. Now, in this particular case, since the diameter of the pipe doesn't change, and we know that dv dt, which is equal to A times V, must also be constant. And therefore, we can say that A1 V1 must equal A2 V2. And if A doesn't change, then V cannot change. So that shows that the velocity must be the same over here and over here. So that means this term and this term are constant. They don't change. In this particular example, of course. Which means that if the height increases, that means that here rho gh2 has increased relative to rho gh1. That means in order for the equation to balance, that the pressure at 2 must be less than the pressure at 1. And that's how you have to read that equation. That's a good way to take a look at Bernoulli's equation when only the height changes and nothing else changes. And of course, because of that, the pressure has to change as well. All right, now let's do an example. Let's say that this height is equal to 5 meters above the reference point, and this height is equal to 10 meters above the reference point. Let's say that the fluid is water, H2O, and let's say that the velocity in the pipe is equal to 2 meters per second. And the question that would be, given the change in the height, given the velocity here, and of course knowing that the velocity there also must be 2 meters per second, what is the pressure at the second point? All right, let's go ahead and do that. Well, first of all, we have an equation. It's balanced. It's left side equals the right side. And since this is constant, that's constant, it doesn't change, we can simply get rid of that part in our equation. Now, solving that for P2, that means I have to take rho gh2 and move to the other side. And of course, I can then flip the equation around, which means that the pressure at point 2 equals the pressure at 1 plus rho gh1 minus, when I bring this across, that would be rho gh2. Simplifying that equation a little bit by factoring out a g and a rho, so this becomes P2 is equal to pressure 1 plus rho g times h1 minus h2. Now notice I did not give you pressure 1. Well, I can put something in there. Just let's say that pressure 1 P1 is equal to 2 times atmospheric pressure. And of course, atmospheric pressure, that would be 2 times 1.013 times 10 to the 5th newtons per square meter. All right, so let's say that pressure 1 was 2 atmospheres. How much will the pressure have changed by allowing the pipe to go up an additional 5 meters from where it was before? All right, so let's plug these numbers in. So this is equal to, I'll leave this at 2 atmospheres for now, plus the density of water. And of course, the density of water is 1,000 kilograms per square meter. So 1,000 kilograms, not per square, but per cubic meter, of course, because it's per volume. G is 9.8 meters per second square. And then we multiply that times H1 minus H2. Now, H1 is 5 meters, H2 is 10 meters. And so very quickly, you can see that that would be a negative number, which means that the pressure will be less at point 2 compared to point 1. Now, how much less? Oh, well, let's find out. So that would be 1,000 times 9.8, that would be 9,800 times 5 minus 10, which is minus 5. So times 5 equals, that's 49,000. So this is equal to 2 atmospheres minus 49,000 newtons per square meter. Now, there's a unit for that we call pascals. So you can say pascals or newtons per square meter. Now, if 1 atmosphere is 101,300 newtons per square meter, what is 49,000 newtons per square meter in terms of atmospheres? So let's do that real quick here. If I have 49,000 newtons per square meter, and we convert that to atmospheres, so 1 atmosphere is equal to 101,300 newtons per square meter. So we can see, if we take that divided by 101,300, one too many, equals, and that would be 0.48 atmospheres. All right, so this can then be written as 2 atmospheres minus 0.48 atmospheres. So we can say this is equal to 1.52 atmospheres. There we go. Now, quickly looking at it again, Bernoulli's equation, we have 3 terms, the pressure, rho GH, and 1/2 rho V1 squared. Notice that all 3, of course, are terms of pressure. If the velocity goes up, then something else has to come down. If height goes up, something else has to come down. So in this case, the pipe gained height. This became bigger since the equation has to stay constant, or the left side and the right side stay constant. If this goes up, that has to come down, and we just calculated by how much. In our next example, I believe it has something where the velocity changes, and see how that affects the pressure in the pipe.